So now I will speak about laws of nature. And I was wondering, because yesterday I was in somewhere, I think it was on Namgyal Monastery, down here in MacLeod Ganj, and I read a wonderful sentence saying that all dharmas are like a reflection, clear and pure, and purely derived from cause. Okay, so you see the idea. Is there a connection between this idea that all dharmas are derived from causes and the idea, say, the Western idea of the law of nature? I think there are some connections, and here again there are differences. The first difference, maybe, is that there are, in the idea of the law of nature, something begins, the world begins, together with all the rules that goes with the world, and then all the rest of the becoming follows these rules that are called laws of nature. Instead, as you know, in the Buddhist idea, there is no beginning. So here is the first difference. Second difference is that laws of nature apply to intrinsically existing things. They apply to massive bodies, they apply to particles, they apply to things. Things that are permanent, have an own kind of existence, and so on and so on. Whereas in Buddhism, as I have understood it, the concept of cause is meant precisely to replace the concept of substance. Because when you say, oh, an event, a dharma, has a cause, this takes into account, and this explains the fact that there are things that are regular, that things happen regularly, that they follow with one another according to something that repeats. You don't need to suppose that there is something permanent that holds this idea of regularity. Regularity happens just by the game of causes and effects without supposing substance. So here is another difference. Another difference also is that laws of nature are rules of succession of events without really asking about the identity of the cause. For instance, if you have, always this phenomenon of fall of bodies, and you don't ask what is the cause of the body coming from that position to that position. You just say, it always happens that when you let a body fall, it falls according to this rule of permanent progression of velocity. So here again, you don't ask about the individual causes, but you just ask about the rule of succession of events. So you see, there are some differences. I think the main difference is the one I'd explained in between, namely that laws of nature apply to substances, to things that intrinsically exist and that are permanent, whereas the Buddhist concept of causality is really a substitute to permanence, to absolute existence. And by the way, just a remark before I come to the heart of the matter. There were some people, some philosophers of science in the West, the so-called logical empiricists of the mid-20th century, who said exactly that. We don't need the concept of a permanent substance, we just need the concept of causality. Causality is enough to account for regularities, for the constant aspect of change, without thinking that there is something permanent and substantial. So there were some affinities clearly between these ideas of the logical empiricists, such as Rudolf Carnap, Moritz Schlick, and so on, and the Buddhist idea of causality. Now, how did things begin? How did the concept of a law of nature begin? Well, the concept of law of nature was clearly born from a theological background. Of course, superficially, a law of nature is a strictly and universally true statement about the regularities of the changes of events. The word necessity is very important. It's not that, when you have a change, it can occur this way or that way. It necessarily occurs this way, the way it is posited by the laws of nature. It cannot be otherwise. And another way to say that in modern philosophy is to say that this sequence of events happens in all possible worlds that are ruled by this law of nature. Of course, there are possible worlds that are not ruled by these laws of nature, but in the possible worlds in which there is this law of nature that were enforced, then things always happen in this sequence. So we say that laws of nature are necessary, or that they necessarily apply. So, as I told you, the origin of the concept of a law is very concrete. It's the idea that, that God imposed the laws, a law that is valid everywhere and always. So it's as if, and you will see later in other philosophers, it's as if there were a king who had a kingdom and he imposed the laws in his kingdom. Also, I think this is also a difference, of course, with Buddhism, because there is no creator in Buddhism. But another difference with Buddhism is that in Buddhism, a cause is preceded by another cause, and then another cause, and then another cause. In this conception of nature, at the beginning of all causes, there is an intention. Okay? It's not a cause. The first cause is not a real cause. It's a project, an intention, and an intention that is meant to create something with rules, with an order. So this is also part of the origins, historical origins of the concept of laws of nature. So here is an example. René Descartes, the French philosopher, he gave a definition of the laws of nature. The rules by which changes happen in nature, I call them the laws of nature. So there was also a modern philosopher, Moritz Schlick, one of the logical empiricists, who said, a law of nature is the constant aspect of changes. The constant aspect of changes. Change is making things different. But there is something that doesn't change, is the way in which things change. And the way in which things change is a law of nature. And as I told you, René Descartes wrote a letter, and he explained very carefully the analogy between God's institution of the laws of nature and a king's institution of the laws of his kingdom. So here is what Descartes said. It is God who established these laws in nature as a king establishes laws in his kingdom. there is known in these laws that we cannot understand. This is very important, by the way. That means that the intellect of human beings is capable of understanding the intellect of God. And this is one of the philosophical requirements for science. If we think that we are not able to understand what God has created, we don't even attempt to understand these laws of nature. And René Descartes adds, these laws are all innate in our minds, as a king would imprint his laws on the hearts of all his subjects. That means that God not only has created the laws, nature with its laws, but has also created human beings who have these laws in their mind, ready to be understood and discovered. So you understand a little bit of this, the theological atmosphere in which science was born in the 17th century. An overview of the laws of nature are George Berkeley's. Berkeley was a British, not Irish actually, clergyman, and he tried to understand the connection between our mind and nature. According to him, in fact, there is nothing else than reflections in our minds. Ideas, as he said, in our minds. And there is God who imprints these ideas in us. So we say that he was an idealist because he believed that there is nothing else than mind and the projections of this mind. For instance, he said that the bodies we see do not exist outside of ourselves, but they are ideas that God has imprinted in our minds. So I think these ideas certainly are a little bit familiar to you because they are a little bit like Chittamatra, I think. Except that there is no God, of course, in Chittamatra. So, according to Berkeley, the rules or methods according to which the divine spirit on which we depend excites in us the ideas of the senses are called the laws of nature. So when God, according to Berkeley, imposes us the ideas of bodies, he also imposes to us the idea of the rules of succession between the states of these fake bodies. Okay? And you see that since, according to Berkeley, the only thing that exists is mind, therefore, God himself is of mental nature. It is a spirit that imposes on us certain ideas, perceptions, rules of connection between perceptions, and so on and so on. Okay, now, I must say, this doctrine, even though this doctrine is one of the ideas that were developed by Western philosophers, this idea is not very popular in the West, and it's usually discarded. Okay, now let's give some example of laws. And you will see that laws are in fact very, very diverse. There is a huge variety of laws. Some of them don't even resemble the others. So this overview of several cases of laws can give you an idea of how the concept of law of nature is wide, very broad. Here is an example of what can be called an inductive law. You remember this morning I said that induction is derivation of the future from the past. And here it's exactly what we do. We observe certain facts, then when we have observed a list of such facts, we try to infer what will happen next. Here is a page of Robert Boyle's observations about the volume, pressure, and even sometimes temperature of a gas. Okay, he took air in a vessel, and he changed the pressure, and he observed what is the volume of the remaining gas after he has increased the pressure. And so here is a list of figures about the volume and pressure of the gas. So column A is the measured volume of the gas, column D is the measured pressure, and then column E is pressure calculated according to a sort of hypothetical law, according to which the product between pressure and volume is constant. If you increase pressure, then volume will decrease. If you increase volume, then pressure will decrease. And the product of the two remains constant. According to this hypothesis, it's a hypothetical law which is called the Law of Boyle. Now, what Boyle observes is that it works. Namely, when you make the product between the measured volume and the measured pressure, you obtain something that doesn't vary. So the hypothetical law seems to be corroborated, as we say. Not verified, once again, corroborated, because there is a finite sequence of facts that fit with this law. And therefore, what do we do then? We say, okay, then this law, we suppose that this law is valid everywhere, at every time, for any gas. And this is Boyle's law. Now, is it credible? Is it credible to infer such universal law from such very small amount of data? Even Robert Boyle was not completely confident, as you read here in the last sentence. He said, I will not venture to determine whether the proposed theory will apply universally and precisely or not. No one currently knows how close to an infinite compression the air can go when the compressive force is increased. I think Boyle was really lucid, because maybe you know that, well, some of you know that, nowadays, or at least from the 19th century, it has been shown that if you compress too much the gas, then the law of Boyle is no longer valid. And you have to replace it with another law. I think it's the law of van der Waals. So why? Because in fact, then I would say, if you want to explain that, it's that if you compress too much the gas, then there is a piling up of atoms, and atoms cannot be compressed more than a certain amount. They become a liquid, in fact. And liquids are incompressible. So this law that has been induced from a finite set of data has limits. And even Boyle was aware of that. He didn't say that this law was absolutely universal. He said, well, maybe, let's try. And you see, once again, first, what is an inductive law, and that it's always a hypothesis, not more. Another kind of law, a law that is a little bit in between, because some scientists derived that law from induction, namely from a list of data, like Boyles, and some of them tried to deduce it from a model of what was going on. So this is the law of refraction of light. Maybe you know what it is. When you have here an interface between two media, say this is glass in below, and this is air. Then there is a ray of light that impinges on this interface, and then the ray of light changes direction. It goes from here, then changes direction. It's no longer this, but this. Okay, and this is called sinus laws because it works according to this law, mathematical law below. I don't know who knows a lot of mathematics, but at any rate, it's a rule to understand the difference of angle between the incident light and the light that is transmitted by glass. Okay, this law, namely the law that the angles of the light agree with this mathematical formula, was derived by a British scientist, Snell, in 1621, out of observation. Just he observed the rays of light, he measured the angles, and he said, oh, that must be this formula. Fine. But here again, how universal is this formula? How necessary is it? Then René Descartes, the French philosopher and scientist, derived the same law a few years later, and but he derived that not by observation, but by calculation from a model. He imagined that light is like a ball thrown on an interface, and that this interface slows down the ball, especially in its horizontal component. And therefore, instead of doing this, the light goes this way. So this was a model. Is it more valid than the inductive law? Here again, it's a hypothesis. And the hypothesis of Descartes was indeed adequately corroborated by experiments. But here again, there are exceptions. And later on, there were new studies that showed that, in fact, the Snell-Descartes law is not absolutely exactly followed because of wave processes and effects. So it's, I would say, Snell-Descartes laws, whether it is induced like Snell or it is deduced like Descartes, is still a hypothesis, and it has to face the future of examinations. So here is a sort of mixed case of inductive and deductive law. Another interesting case is the laws of motion of Newton. And one of these laws is really special. It has no equivalent, and it's really revolutionary. It's the first law of Newton, the so-called law of inertia. The law of inertia says, as you see from Newton himself, and it's really, you know, this page is drawn from his famous Principia Mathematica de Philosophia Naturalis, which means mathematical principles of natural philosophy. You would say mathematical physics in modern terms. Now, the first law, everybody perseveres in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by forces impressed. So, the idea is that when you leave a body to itself, motionless or uniformly moving, nothing new happens unless you exert a force on it. Okay? And the second law is precisely about the effect of forces. Now, this law is really special. Why? Because, first of all, it says nothing. It just says things do not change if you do nothing. There was a famous sentence by Galileo, I will allude to that later. Motion is like nothing. Namely, it's not a special state motion. You cannot detect that you are in motion or at rest because when you are moving with a body in motion, things happen exactly as if you were at rest. Now, you know that this is very counterintuitive because usually when you first push a body, it stops on Earth, at least. Okay? And Aristotle said that it was indeed the case, and therefore, in order to set something in motion, you always have to exert a force. And even to maintain something in motion, you have to exert a force. But Galileo said, no, that's not true. You don't need a force to maintain motion. You have to have a force to impel motion, but not to maintain motion. And Newton, of course, catched the idea of Galileo and turned it into a law. So how did they come to this conclusion? Because actually no one could observe that a body that has been set into motion continues motion without stopping, without ever stopping. If you see anything on Earth, it's not true. Any body stops at a certain point. We would say because there is friction, okay? There is air and there are many other causes of friction and therefore the body stops. So in order to derive such a law, you had to perform an idealization. I will come to that later. This cannot be a law of induction because you never see a body that has permanent motion. It cannot be experience that teaches us this. So it is an idealization of experience. You imagine that there is no more air, that there is no more friction, that the ball is going in vacuum, and so on and so on. Okay? So here you see a law that is neither an inductive law nor a deductive law. It's a general principle that is used in order to derive other laws, and that is based on a complete idealization of phenomena. So really a different type of law. And still, all these things are called laws, you know. Here is a fourth type of law. Classificatory and statistical type of law. Mendel's law. You certainly know that. The laws of Mendel about genetics. Probably the first genetical law ever in history. So it was done in the mid-19th century. So according to this law, you have four possible features. So the color, either yellow or green, the aspect of the surface of peas, either rugged or smooth, and you combine. So how many of them are green? How many of them are yellow? And you obtain, you obtain a proportion that is approximately 1/4 and 3/4. But, you know, in the experiments of Mendel, the proportion was not so clear. It was a little bit like, yes, 1/4, but a little bit more or a little bit less. And he posited that it should be exactly 1/4. Why? Because he had a model. And the model was the model of the difference between regressive and dominant genes. And And this model imposed the precise proportion 1/4, 3/4. So here you have a law of proportion which is more or less induced, but in fact it's more deduced than induced. And then it became a normative law, namely when you find, when you count the aspect of p's, you must have 1/4, 3/4. If not, you are wrong. You have counted wrongly. So it became, and you have to come back, or there is a disturbance, or you have had some bad weather or anything. Okay, so it became a normative law about the proportion of aspects of p's. So now we have 4 examples of law, and very different types of law, and very different also types of things on which the laws apply. Maybe, the law can apply to events, namely it imposes that events should follow each other in a certain way, or it could be imposed onto classes or universals, for instance, the classes of yellow peas or the classes of rugged peas, things like that. Or it can act on potentiality. The type is, if we do this, then it will happen that. But if we don't do that, nothing happens. And therefore, you cannot say that some regularity has happened independently of what we are doing. For instance, a very good case is quantum physics. Quantum physics doesn't have laws that are completely independent on what we do. Only one law, by the way, is independent on what we do, but it's a very strange law, you will see. It's called the Schrödinger's equation, and it rules probabilities. Probabilities are guesses, okay? But all the rest is dispositional, namely, we say, if we do this kind of experiment, then we'll get, with a certain probability, this or that result, okay? So events, classes, potentialities. Not only laws of nature are different from each other, but they have different topics or different objects. But in fact, these objects entangle, so to speak. First of all, beware. When we say a law bears on events, in fact, they don't bear on particular events. They bear on classes of events. For instance, the class of events of free falls of objects. It doesn't bear on this free fall of objects. It can be checked by this precise occurrence of a free fall of object, but it doesn't bear on this or that case. It bears on the general class of events called free falls of objects. For instance, I love this quote by the French mathematician Henri Poincaré. He said that a physicist would say, King John stayed here, but I don't care, since he won't come here again. What does it mean? It means that a physicist doesn't care about particular events. He doesn't care about historical facts, because these facts are unique. He cares about classes of facts. He cares about the fact that each time this occurs, then that will occur. Each time. Each time is a crucial term here. But, of course, in order to check these general laws that apply to classes of events, we have to have particular events. It's only if we confront this general law with particular events that we can say that we have tested the law. Okay? So there is a connection between generalities and particular cases, and this connection is the connection of testing the theory or testing the law. Now, when I said that law has, for instance, according to certain philosophers, a law is not much more than what they call an economic summary of facts. The positivists of the 19th century, such as Ernst Mach, said that a law is only an economic summary of facts. Instead of saying, instead of giving all the lists of these figures that you saw in Boyles' page, you just state PV equal constant, and that's a summary of thousands of figures, okay? You could also call that, in more modern terms, an algorithmic compression of data. Namely, you give an algorithm, namely a way of calculating, that automatically generates thousands of data that we can compare with actual measured data. So you compress the data into one formula. So it's beautiful. It's, at least it has something appealing in it because you save memory. But beware, this is a usual way of stating law of nature by empiricists or positivists. But beware, because a law is not only that. It's not just a summary of data. It's much more than that. It's a claim about the future. A claim that in the future, things will occur exactly as the law says, not just a summary of past data. So in that sense, a law is a guess. It's a gamble, because it says something about the future that will have to be tested. So how can we reach this generality of laws? Yes. Here again, maybe I can give also a bridge with Buddhism here, because in Buddhism, especially in Buddhist epistemology, Dharma Kirti and so on, the general concepts are something that are less close to reality than the particulars. For instance, there is a difference in Dharma Kirti between, I say that in Sanskrit, between Svalakshana and Samanya Lakshana. So Svalakshana is sign of itself. It is for something that occurs one day at a certain point and here and now. An event, so to speak. Whereas Samanya Lakshana means something together, namely a concept. And according to Dharmakirti, the Svalakshana is much closer to ultimate reality than the general concept. Instead, science, modern science, always look for more generality. And people, usually scientists, say that the more you have unified a set of data in a general law, general concept, general formula, the more you are close to reality. So you will see, I will tell you more later about the difference between science and Buddhism, but this is a very huge difference, I think. The idea of reality is almost opposite. So how can you reach this level of generality, abstraction, universality, and so on? First of all, as I told you, by idealizing situations. The principle of inertia, this first law of motion of data, was obtained by isolating a body in thought, by imagining an infinite space for its motion, because usually a motion is limited by a room, limited by the earth, limited by anything. Here instead, the idea is that there exists a scene for motion that is limitless, boundless. And you imagine that, because there is no such thing in practice. But you imagine that, and you say, if a body was left to itself in empty space, and if this space was not limited, then there would be permanent motion. Also for falling bodies, the law of acceleration of a falling body needs the absence of air. If not, it doesn't fit. And therefore, there are experimental idealization. For instance, you place the bodies in a vacuum. You construct a vessel, you extract the air by a pump, and then you study the fall of the body in vacuum. If you don't do that, the law of Galileo and Newton doesn't work. Okay? So it's interesting because a modern philosopher of science, Nancy Cartwright, said laws of nature always need excuses for not being in force. If you see that the body doesn't fall according to the law of acceleration of Galileo and Newton, you say, oh, that's because there is air, okay? Or there is friction, or there is the attraction of planets, and so on and so on. So laws are idealization. They work only in an idealized experiment and idealized world. You need also abstraction from events. For instance, instead of an indefinite variety of occurrences, you impose a discrete classification, namely either rugged or smooth, either yellow or green. But when you see carefully the peas, some look yellow-green, some look, we don't know if they are rugged or smooth, and so on. So in order to do a proper law, you have also to abstract, to say, no, there are only two classes, either rugged or smooth, nothing in between. Okay? So a lot of abstraction, idealization, generalization, and so on are required in order to get the law of nature. Now, what about the so-called necessity of the laws of nature? The fact that they hold everywhere, in any circumstances, for anyone, and so on. Well, this is not so obvious, because, for instance, some philosophers like Hume, David Hume, this famous Scottish philosopher of the beginning of the 18th century, said that no, there is no necessity in the so-called laws, that we just observe that there are regularities, and we have no guarantee whatsoever that the regularity will hold later and for other people in other places. So it's just an observation and nothing more. But other philosophers, probably closer to the ideals of science, wanted to impose the famous necessity of the laws of nature. So how did they do that? Well, there are two ways to impose the necessity of the laws of nature. First way is theological, once again. The second way is epistemological, namely it has to do with the methods we use in order to know something. So first of all, Leibniz. Leibniz, German philosopher of the end of the 17th century, tries to understand the necessity of the laws of nature by way of his idea of how God should have done the world. So he distinguishes three types of necessity: the strict of logical necessity, the physical necessity, and the hypothetical necessity. First of all, logical necessity. A necessary truth is a proposition whose opposite implies a contradiction. It is a proposition valid for all possible worlds. Okay? For instance, laws of logic are of this type, you know. There is a case which is very interesting. You imagine someone who claims there is no truth. Imagine, I claim there is no truth. And someone here asks me, how? And is your statement a truth or not a truth? Okay? So if I claim that my sentence, there is no truth, is true, then I'm contradicting myself. Okay? And if I'm not claiming it's true, okay, I've lost. Okay? So this is the kind of extreme necessity in propositions. This is just an example, but there are many others. Also, the physical necessity. Physical necessity is quite different from the logical necessity. You know, according to Leibniz, God cannot avoid to follow the rules of logic because they are absolutely necessary. They don't even depend on him, very interestingly. But physical necessity is different. It imposes itself on God when he chooses to create one of the possible worlds. He says, okay, I want a possible world. Among all the possible worlds, I want to select the one which has most perfections. And therefore, I select this one. And this selection gives rise to what Leibniz called physical necessity. God didn't have to choose this world in the absolute, but he had to choose this world just because he is good and wise, and he had to create the best of the possible worlds. Okay? This is the idea. Okay? I have to enter into a very different mentality here, but this is how the concept of law of nature was born in history, so it's very interesting to know. Hypothetical necessity imposes itself on human beings when they are confronted with a temporal sequence of events. Namely, one event necessarily follows the other one. But that the first event existed was not necessary. Maybe it was just created like that by God, and then the follow-up was necessary, but not the first one. Okay, so now we see some sentences by Leibniz who explain this idea of physical necessity. So I read, since there are infinitely many possible universes in the ideas of God and there can only exist one of them, there must be a sufficient reason for the choice of God which determines him to choose one rather than another. And this reason can only be found in the convenience or in the degrees of perfection that this world contains. Okay? That means that God must have had a reason to select this world. And the reason why he selected this world is that the world is most perfect. That's it. Although the world is not metaphysically necessary, or no, so that the opposite implies contradiction or logical absurdity, it is, however, physically necessary or determined, so that the opposite implies imperfection or moral absurdity. It's the same idea. This world was not absolutely necessary, but it's to some extent necessary, because if not, there would have been something bad occurring in this world. For instance, let's suppose this world has had no laws. So this world would violate what Leibniz calls the principle of sufficient reason. Nothing occurs without a reason. Secondly, this world would have been unruly, disordered, and therefore less beautiful and less good than the ordered world we observe. But this conception has triggered some jokes from other European philosophers. For instance, the French philosopher Voltaire said that it was absurd to say that God had selected the best of the possible world. And he was taking the example of the earthquake in Lisbon, in Portugal, that killed 100,000 people who were presumably innocent people. And he said, how can you believe that God created this world according to its degree of perfection, while it can host such horrible things? So this idea of the best of the possible worlds was very, I would say, controversial. What does it mean for laws to exist? It means that they are part of the package of the best of the possible worlds. Laws are physically necessary because a world without a law would not be perfect. And here is what Leibniz said. To be the best for the world that exists means to be the simplest in its laws and the richest in phenomena. So here you have a very important idea. Not only the world must have laws in order to be perfect, but the laws must be the simplest in form and the richest in phenomena that they can produce. So all these ideas of best, maximum, minimum, you see, a law is the simplest, a law should bring the maximum of phenomena so that the world is richer, more interesting, and so on and so on. This is very important. Leibniz's ideas are principles of optimum, the best, or the maximum, or the minimum of complexity, and so on and so on. The most perfect in every dimension. The wisdom of God, said Leibniz once again, made him choose the laws of movement best adjusted and most suitable for abstract and metaphysical reasons. So reason is important, but the reason of God commanded him to choose these particular laws because they are the best. And we humans can do something to understand what was in the mind of God. Now, why are there laws rather than no laws at all? The absence of laws, I told you that, the absence of laws would imply that something can exist without conditions. In other words, that something exists without having any reason to exist. Now, this is also something interesting because, you know, the principle of causality in Buddhism is posited as, you know, a fact. Here there is an attempt to justify it by the wisdom of God. God could not have made a world in which things happen without reason, because it would have been contrary to the working of reason, which is the best possible way of organizing the set of events. So there is, I would say, a reason to the existence of reasons. But here you can understand that there is a sort of infinite regress that is involved. Because, okay, there is a reason for the existence of reason, but why is there a reason for the reason of the existence of reason, and so on and so on. The same kind of, question that one could raise. Okay, the fact that God created the world explains the world, but why was there a God rather than nothing? What is the explanation? So there is a point at which all explanations stop. And maybe it's the merit of Buddhism of having well understood this and said, okay, there are things that we should not try to explain. This is the famous Buddha saying that when you see an arrow planted in the flesh of someone, you don't go too far into explaining metaphysical reasons and so on. You just try to do something out of what is given to you. Here, so you have here two attitudes. One that tries to go further and further and further into the chain of reasons, one that tries to derive the best from what is given to us. However, I must say, Leibniz's principle of the best possible world has been very fruitful in the history of science. Here is a case, an interesting case, in which a conception, an abstract metaphysical conception that has no real credence, no certainty, it's not really evidence-based. The idea that God created the world according to the principle of the best is not really grounded in anything, But it has been fruitful in the history of science. It has suggested to some scientists, the first one being the two French scientists, Pierre Fermat and Pierre de Maupertuis. These two scientists said that you can derive the laws of nature according to the principles that the path that is derived, the path that is followed by a body must be the shortest possible or take the less possible time. You can even derive the famous refraction laws, the law of sinus that were derived by Snell and Descartes, from a principle of minimization of the time that is taken by light to go from one point to another point. Okay? So this idea that the world was the best possible world had a non-religious consequence that was the principle of minimization or the principle of optimum from which you can derive laws. By the way, now we can make a huge step in time and go from Maupertuis, 18th century, to present day, standard model of elementary particles, and you will see that this principle of minimization is still in use in this form. I don't explain this form. In this form, it is in use everywhere in physics. Physics uses this principle to derive all its laws. So this principle of minimization or optimization is really a universal tool of physicists. And it derives historically from the idea that God created everything as an optimum. Now, I must say there can be other explanations, of course, than God's in the efficiency of this class of, I would say, principles for the derivations of laws. There are other explanations, but I think we should maybe take a little pause at this moment and have tea. Is it? Okay, you have seen that the origin of the laws of nature was very much theological. It has to do with God, creation, perfection, and so on. Yet, you have seen also that these theological concepts became tools for physicists. The physicists almost forgot their origin, and they used them. They didn't care about the fact that Leibniz said that the laws of nature were created by God. And they used these concepts very fruitfully. But so that's very interesting to see that a philosopher of the last half of the 18th century, Immanuel Kant, one of my favorites, by the way, tried to disentangle the concepts of law of nature from their theological origin. And he tried to see how you can conceive of the necessity of the laws of nature without thinking that God has imposed them. Okay, so according to Kant, the laws are not there just to be picked up by us. They are, to a certain extent, imposed by us on phenomena by our understanding, by our minds. Why? It sounds strange, you know. Laws of nature cannot be laws of our mind. There is a difference between them. But beware. According to Kant, you know, if we live in a world with completely disordered phenomena, we would not even have the concept of objects, not even have, of course, the concept of a nature. It's impossible. We would just be like babies, completely exposed to the variety of sensations without being able to organize them into clusters that we can call objects. So in order to do that, in order to organize all this amazing richness of sensations, perceptions, into wholes that can behave as if they were independent of us, we impose laws to these events. Or rather, we impose these laws as filters, namely, all the phenomena that go through the filter of our understanding are taken as something that can be ascribed to nature. Let me give an example. Causality. Causality is absolutely crucial for everyone, for Buddhists, but also for Kant. Okay? Causality. Okay. You see various phenomena. You see various phenomena, but this variety of phenomena can be due to many factors. For instance, I can see up, and I see a different phenomenon from what I see here. Or I go in darkness, and I see completely different phenomena than the ones I observe here in this room with light, okay? So you see that here the change in phenomena is due to the changes in my perception. Or I can be ill and see things all yellow. Or, you know, many things can happen due to us, to the fact that we change. So how can we disentangle the changes that can be said to belong to us from the changes that can be said belong to objective nature? In order to make this disentanglement, we need to say that only the phenomena that follow from each other, according to the law of causality, are taken to be objective. Only them. If a phenomenon changes because I close the eyes, I don't say it's an objective phenomenon. It's a subjective phenomenon. Okay? So the law of causality is used by our understanding to divide the phenomena between objective and subjective. So you see that at the beginning, I would say, at the beginning there is no distinction between subject and object. No one. But if we want to impose one, we have to impose the law of causality. The law, every phenomenon that follows the law of causality is a phenomenon that can be said objective. Every other phenomena are not objective. So it's a sort of filter, you know. Causality is a filter for discriminating between objective and subjective. So the law of causality is not a law that belongs to nature out there. It's a law that makes it possible for us to think of nature as if it were separate from us, namely as if it were objective. I hope you follow this reasoning. It's a little bit difficult, I think. Yeah? It's difficult because, you know, it's very subtle. It doesn't take the separation between subjects and nature for granted, but it shows how we elaborate it from a set of indiscriminated phenomena. We make a divide. All those which follow the law of causality are said to be objective. All those that do not follow the law of causality are said to be subjective. Very simple. Okay? So, according to Kant, you can express that this way. The law of causality is not a law that belongs to nature out there independently of us, but it's a law that we impose in order, I quote him, to constitute an objective nature. To constitute an objective nature. Okay? Because at first we don't have an objective nature. We have all this richness of phenomena that come on us, that we live, that we experience, okay? And then we make the difference and we constitute an objective nature. Do you have a question about that? Because it's really a difficult point, but I think a crucial point. So if you have a question, a doubt, a qualm, or anything, please ask. Well, this is the conception of Kant I'm exposing. It's really special because, you know, he says that it's no longer God. It's human beings with their experience. How can they try to make the difference between what is internal to us and what is due to nature, to objective nature? How do they do that? They impose certain principles of our understanding, and as soon as they have done that, as soon as they have filtered out what obeys these laws of understanding, they say, oh, this must be something objective. Or at least, maybe I have to express that more carefully. They don't say, oh, that means that there is something objective out there. No, they say, the only way I have to speak of objectivity is by imposing rules on what happens. Everything that happens according to a rule behaves as if it were objective, as if it were objective. Okay? Everything that doesn't happen according to this rule is the fantasy of my subjectivity, or the accidents I can have in life, and so on and so on. And this I rule out and say, this is all subjective. Okay? So you see how Kant thought that it's possible to create the duality between objectivity and subjectivity from an experience that is fundamentally non-dual. Okay? This is what is very important to understand. So these laws of nature are not laws of nature because they belong intrinsically to nature, but because they make nature possible, because they constitute nature. Indeed, according to Kant, nature is nothing other than the succession of phenomena according to necessary rules, namely according to laws. Okay? he defines that. He defines nature as the succession of phenomena according to laws. So you cannot say, here again, that nature has laws, but nature is defined by laws. Okay? It's defined by us according to laws. So God created nature in the old philosophies of Leibniz, Berkeley, and so on, but human beings constitute nature according to Kant. This is, of course, constitution doesn't mean creation, of course. But this is a very interesting teaching of the philosophy of Kant. The philosophy of Kant is an attempt to remove God from the picture and put, to a certain extent, human beings instead. It's very strange, very interesting. So human beings now, with their reason, play a little bit the role that God played before. But here again, constitution of nature doesn't mean creation of nature. Something is given to us. We didn't create it. What is given to us? Experience, phenomena, what we live now, here. But we try to discriminate and we push aside all that is really on the side of objective nature and what is unruly on the side of subjectivity. Here is, I hope you understand. But okay, so what does Kant say? The word nature already includes the concept of laws. Here again, it's not that it's the laws that are imposed onto nature. Nature is constituted by the concept of law. You understand? And therefore, for instance, the laws of causality and permanence of the substance. Here again, Kant didn't claim that there are substance in the world. He didn't claim that there are things that are permanent. But he said, in order for us to grasp something that we can consider as if it were objective, we have to posit some amount of permanence on the clusters of phenomena we see. That's it. And so the laws of causality and permanence of substance are called the transcendental laws of nature. Here again, maybe you are scared by the word transcendental. But the word transcendental, it doesn't mean anything far away, beyond, and so on. It just means the background conditions of possibility for us to discriminate between nature and us. Okay? So, causality and permanence of substance are laws in a very, very deep sense. They are not laws because they belong to nature. They are laws because without it, the concept of nature would not even be possible. We need to impose laws in order for us to think of something like nature. So, the fact that the laws are necessary takes on a very different meaning, of course, in Kant and Leibniz. Since in Leibniz, the necessity, the so-called physical necessity comes from the fact that God tries to reach an optimum, perfection, whereas, of course, in Kant it cannot be that, because Kant has removed God from the picture. The transcendental laws of nature, namely causality and permanence of substance, are necessary neither because of the principle of contradiction, nor because of the principle of the best applied by God external to nature. They are necessary in nature because they are constitutive of nature. Very simple. In some way, it's very simple. In another way, it's a little bit difficult. Okay? These laws cannot it cannot be the case that they don't belong to nature, because without them, nature, the concept of nature, would not even be possible. Okay? Without these laws, we would not even find meaning to say that there is a nature. Only there would be just a disordered set of appearances. By the way, you know the Greek word cosmos. When you use cosmic, cosmology, and so on. Cosmos. Cosmos is translated by universe or world in English. But cosmos meant something different in Greek. Cosmos meant order. Okay? So the very meaning of the word world includes the notion of order. Without it, there would not be a world. There would be a game, a playful game of impressions that would not even stay in us and be forgotten immediately. Okay? So the order is the condition for the existence of something we can call a world. Now, is this idea of Kant fruitful in science? I've inquired into that because I think it's very interesting. Just in the same way as Leibniz's idea that God creates the best of the possible worlds have had a tremendous influence in science, because now there are these principles called the principles of least action that are used everywhere in science, that are used especially in physics. But what about Kant's idea that the laws of nature derives from the conditions of possibility of nature that we need in order to have the concept of nature? Do you believe it has an effect? Who believes it had an effect on physics? Yes. You don't believe that? You have difficulties believing it? This idea that the condition for us to believe that there is a nature has an effect on the laws that are ascribed to nature by physicists. It's very strange. That means that we are very much involved in the process and we don't know. Okay, I give you an example. A tremendous example, one of the best, most remarkable example in the history of science. It's called, maybe you have heard of that, maybe not. It's called Noether's Theorem. Noether. Noether. N-O-E-T-H-E-R. Emmy Noether was a German mathematician, a woman living in Germany at the beginning of the 20th century. And she established a theorem that is absolutely essential to understand modern physics. What does this theorem say? Let's suppose you impose to the laws of nature, you accept that there are laws of nature, but you don't know which one. Okay? You impose to the laws of nature to be the same irrespective of the place, of the time, and of the state of rotation, of the direction. Okay? This is just a definition of what is a law. Because if a law is a law, it must be valid everywhere. It must be valid in Toronto, in Dharamsala, in Delhi, anywhere. So, Noether posits a law must be invariant by translation in space. It must be invariant by translation in time. It must be the same in the 17th century and now. The laws of Newton have not varied. It must be also the same irrespective of your direction. You know, the laws of motion are valid irrespective of if you see here or that, okay? Okay, 3 statements, very simple. Laws must be invariant by translation, modification of time, and rotation, okay? Now, Eminota demonstrated by difficult mathematics, but not too difficult, that if you posit these 3 conditions, you must have conservation of energy by the clause that the laws must be invariant in time, conservation of momentum by the clause, momentum, you know, is the product of mass by velocity, by the clause that laws must be invariant by translation in space, and conservation of angular momentum. Well, I don't explain what it is. If you posit the condition that laws must be invariant by rotation. The basic laws of nature derive from 3 clauses that just say there exist laws of nature. If you want the laws of nature to exist, then these laws have the form they have. Conservation of energy, conservation of momentum, conservation of angular momentum. Isn't it extraordinary? Just asking something that is good for us, namely positing laws of nature, is enough to derive the laws of nature. This is exceptional. I can quote you many other examples, but if you understand that, you have understand why Kant was very, very, very clear-sighted, because he understood that the form of the laws of nature derive from what we need to posit in order to have an order in our environment, so that we speak of a nature. Okay, so it's very, very remarkable. Okay, but more recently, there has been doubts. Are there really laws of nature? Can we speak of laws of nature? You understand, what in the evolution of ideas, you started with these guys who said God has created a kingdom that is called nature and has imposed rules on it that are called laws of nature. Then there was Kant, who tried to recapture all the role of God and give it to human beings. But in a certain way, he kept the idea of a law of nature and just ascribed human beings the role of formulating these laws. But there are, you know, in later thought, later philosophical thought, there are even more drastic criticism of the initial concept of law of nature. It's the case, for instance, of the 2 modern philosophers of science, Bas van Fraassen and Nancy Cartwright. According to Bas van Fraassen, there are no laws of nature, but laws of models that guide us in action. He'd say, well, I don't know about nature. I know nothing about nature. But what I know for sure is that my scientific theories have laws in them, and that these laws help them build models, and that these models guide us in action. And that's it. Laws are no longer laws of nature, they are laws internal to our models. It's not so far from Kant, in fact, because Kant thought that the laws were our laws. And according to Bas van Fraassen, laws are the laws of the models of science, not laws of nature. And Nancy Cartwright also has her arguments, but maybe I will skip them, because I think Bas van Fraassen is really much more important to understand, because he makes you understand that after all, when you call a law of nature. It's just because it's a law that is inner to a model of science, and that this model of science has shown capacities to account for many observations. That's it. Do these laws belong to nature or not? It's something that we should not try to understand. They just belong to the model, and the model is corroborated to a certain extent, and then we are satisfied. Sometimes, another doubt that came recently, very recently. Maybe you have heard of the idea of dark matter. Who has heard of dark matter? Not so many people. Not so many people. Okay, so it has been, a commonly accepted knowledge during the past 20 or 30 years, but less and less now, by the way. But during the past 20 or 30 years, that the world is composed of visible matter, but also dark matter. What is dark matter? It's matter that cannot be seen, yet has a gravitational influence. It attracts bodies like visible matter. Okay, why did people believe so? Because they observed these things, galaxies, and they measured the velocity of rotation of the stars around the nucleus of the galaxies. They measured that, okay? And according to the law of Newton, and even according to the law of Einstein, by the way, the velocity should decrease with increasing distance with respect to the center of the galaxy. Okay? So the more you are far from the galaxy, the less the velocity of your star should be. Okay? Around the center of the galaxy. But this was not observed. So this was not observed. What we observe, but what scientists observed is this law, B. Namely, velocity doesn't vary according to the distance to the nucleus of a galaxy. How can we explain that? Here is an interesting fact. You have a prediction from a theory, even from the two best theories of gravitation we have, Newton's and Einstein's. Both would predict A without any hesitation. And we observe B. Completely different, nothing to do, extremely different. How can we account for that? You see the kind of situation in which scientists can be. They don't know, they doubt, they are completely lost. How can we explain? Well, should we abandon the theories of gravitation? It's quite hard because the theory of gravitation account for a lot of facts around our Earth. They are also applied to understand many facts very far from us in the universe. And so it's a little bit terrible to abandon such beautiful theories. So 20, 30 years ago, scientists said, okay, no problem. We can explain this anomaly of the velocity of stars around the center of the galaxy by imagining that the galaxy is filled uniformly by a new kind of matter, and since we cannot see it, we call that dark matter. Okay? So they invented dark matter to save the theory, I would say. All the best theories we have. So they say, now, what is scientific in this supposition is that they accepted that the hypothesis can be falsified. And they said, okay, now we should look for these dark matters and if we don't find it, so well, so good. We will renounce it. And they looked desperately for dark matter. They used particle accelerators, made lots of hypotheses about what this dark matter can be, neutrinos, supersymmetric particles, very heavy abnormalous particles, and so on and so on. And they looked for them in their accelerators of particles. And by the way, 30 years after, they didn't find anything, nothing. And there are even good reasons to think that some of the superpositions that were done to account for dark matter are completely dismissed. So nowadays, very recently, people started to doubt maybe this dark matter was just a trick we used in order to save our theories of gravitation. Maybe we should change our theories of gravitation. And the whole new industry in science started to modify the theories of gravitation, especially at far distance. So the most elementary version of it is called modified Newton dynamics. It just, you see, Newtonian dynamics should be this formula, but without the bracket, without A over A0. So it's just this little term that has been introduced to modify the law of gravitation. But, you know, the law of gravitation was well established for many reasons, and therefore it's always very difficult to accept just such an ad hoc modification of the law. So now that we believe that probably it's the law of gravitation that should be modified, now many physicists try to show that this kind of modification can come from elementary first principles, and not just because we want the right result to occur. Okay, so now we are in the process. Okay, but it's interesting because it's a case we are living now at this moment, and we see how you know, a law of nature can be threatened by new observations, but not immediately. At first, we try to save the old law until we see that it's really impossible to save it. And then we accept, we say, okay, we'll try to modify the law, but then when we try to modify this way, namely just adding a term that fits, that works, we say, oh, we are not satisfied. We should try to derive that from something that is more fundamental and could explain many more facts than just this one. So you see all the process: doubts, reconstruction, hypothesis, attempt to unify, to reconceptualize, and this is the work of science, I think. Okay, so maybe we could stop here and please ask many questions. Yes.
So how would you describe the stage at which the physics community is at understanding like the outer space as well as like the quantum level, at the quantum level?
It seems like those two things are the ones that are the most difficult to understand, more nuanced. So what stage is the physics community at in understanding space and, I guess, quantum mechanics?
Yeah.
Like,
huge question. Yeah, well, you know that there are two main physical theories. The one is the general relativity of Einstein, formulated in 1915, and that claims that in order to account for the gravitational phenomena, namely planets rotating around the sun and so on, we have to accept that space is curved. And planets follow the line of less distance in this curved space. So this is the theory of space-time. Okay? It's general relativity, and it accounts for phenomena of gravitation. On the other hand, you have quantum physics, which is completely different. It has nothing to do with that. All the concepts are different, but it accounts for all the rest of the phenomena, not gravitational, but all the rest. And you know that the problem nowadays is to unify the two theories, because here again, scientists like unification. Is it a prejudice or not? I don't know. They like unification. There are old cultural reasons for that, but there are also practical reasons. The old cultural reason is that we want everything to come from a single principle. We want everything to, we want, probably our unconscious says, the mind of God is simple, and therefore the principles should be simple also, and they should be one. Okay. But there is also a practical reason. The practical reason is that the more a theory is unified, the more it's testable. Because if you perform a test on one aspect of the phenomena, it's able to test all the theory at once. Only one fact can destroy a theory. Instead, if you have 1,000 theories, one fact destroys one of these 1,000 and not the others. So being sensitive to test is a crucial quality of scientific theories, and I think this is one of the practical reasons for this urge to unification between theories. So now, do we really, you see that the fact that we cannot still unify these two theories is felt by many scientists as a sign that we don't understand everything. We are far from understanding everything. So they wish to understand more, and the sign they will take as, as evidence that they have understood something is that they can unify these two physical theories. And then, do we understand quantum physics? Maybe I'll say that tomorrow or after tomorrow. It's not very obvious because you have certainly heard that still nowadays in quantum physics there are many very different interpretations. The tale we tell about the world is amazingly different from one interpretation to another. And I'll show you that there are even interpretations in which we should not even tell a tale about the world, according to quantum physics. So it's not, I think that our understanding of quantum physics is still controversial. I don't say it doesn't exist. It's still the topic for debate, controversies, and so on. Personally, as you will see, I have an idea shared by many philosophers and physicists across the world, and I'm really convinced it's a good one. But since there are other possibilities, I must say no, we are still in the verge of, in the process of understanding. We are still not very clear about that. Thank you. So see you tomorrow. Thank you.